Imagine trying to fit your entire software development environment into a space smaller than a single low-resolution JPEG. I mean, your compiler, your text editor, your operating system, and all your hardware drivers.
Right. Most engineers would look at that requirement and just say it's physically impossible.
Exactly. Because if you want to write a simple program today, just to blink a light or read a basic sensor, the standard operating procedure is to pull in gigabytes of toolchains. You've got megabytes of dependencies and these massive towering abstraction frameworks.
And we've just been conditioned to accept that bloat as the cost of doing business. The embedded software industry has layered so many abstractions, hardware abstraction layers, middleware, real-time operating systems, that developers rarely even touch the raw circuitry anymore.
But today, we're stripping all of that padding away. We're going to look at an architectural landscape that is the absolute definition of extreme bare metal engineering. We're talking about a programming language ecosystem where the compiler, the interpreter, the assembler, the text editor, and the command shell all fit into a microscopic 20 kilobytes of memory.
It really is wild, and it's not just a toy either. It runs fast enough to beat modern mainstream embedded languages in a foot race.
Yeah, and for you listening, if you write in C or C++ or Rust, you know that 20 kilobytes is a remarkably small footprint.
Right.
Compiling a simple Hello World application with standard libraries using, say, a modern GCC toolchain, that often exceeds 20 kilobytes before you even add any actual business logic.
Oh, easily. It absolutely bends the mind a little bit.
It does, and this 20 kilobyte marvel is the subject of our deep dive today. It's called Mecrisp-Cube. Specifically, the variant we're analyzing is running on a dual-core ARM Cortex-M4F processor.
Right, and for the hardware enthusiasts listening, that is the STM32WB5ART-RG chip.
Yeah, that's the one. And what makes the system so fascinating to me is that it forces a collision between two completely different engineering philosophies. It merges a radically optimized native code fourth compiler, which is known as Mecrisp-Stellaris RA, with the highly complex, massively abstracted STM32CubeMX hardware ecosystem.
Which means it takes the purest, most uncompromising approach to software construction and literally bolts it directly onto modern hardware features that usually require massive, heavy drivers.
Right.
We're talking about integrating a native fourth environment with a real-time operating system, a Bluetooth 5.0 stack, USB connectivity, hardware floating point math, and a FAT file system.
All of that. And our mission today is to unpack the nuts and bolts of how it actually achieves this. We're going to dissect the crown jewel of the system, which is its intensely optimized register allocator.
That's the engine room right there.
Exactly. We'll explore the assembly-level optimizations that make this tiny footprint execute at near C speed. But we are also going to look at the dark side of this architecture. We'll contrast the incredible power of interactive hardware debugging against the terrifying risks of relying on handwritten assembly state machines.
State machines that have absolutely zero automated testing, I should add.
Yes, zero, which is a huge point we'll get into. Ultimately, we need to answer a core question today. Does a system like this belong in a STEM classroom, a hobbyist's garage, or a professional commercial engineering firm?
It's a tough question to answer.
It is. So if you're a developer who writes Python, Rust, or C for a living, and you've ever felt overwhelmed by the sheer weight of modern tooling, this deep dive is going to fundamentally challenge how you view software architecture.
I think the best place to start is with the performance paradox. Because to understand why Mecrisp-Cube is so brilliant, we first have to understand the inherent mechanical disadvantage of the language it's built on.
Right, because Forth is a stack-based language.
Exactly.
Which means, unlike C or Python, where you assign values to named variables like X or Y, Forth pushes everything onto a central data stack. So if I want to add two numbers, I don't write X plus Y.
Right, you push the first number onto the stack, put the second number onto the stack, and then you call an addition function.
And that function automatically pops the top two numbers off, adds them, and pushes the result back onto the stack.
Fundamentally, yes, that's how it works.
Yeah.
But physically, down at the silicon level, that creates a severe performance bottleneck. Historically, a stack is just a designated block of RAM random access memory.
Right.
And compared to the internal registers physically located inside the CPU core, accessing RAM is agonizingly slow.
So every time a traditional Forth system pushes or pops a value, the CPU has to reach out over the memory bus, initiate a read or write cycle to the RAM, and just wait for the data.
Exactly. If you're executing a complex mathematical loop, you are constantly touching RAM. It's a massive mechanical penalty.
Let me try to put this into an analogy. If we think about the CPU as a chef in a kitchen, A traditional stack implementation means the chef has to walk all the way across the kitchen to the pantry, which is the RAM for every single ingredient.
That's a great way to picture it.
Yeah, so you need salt, walk to the pantry, you need pepper, walk to the pantry, you need to mix them, walk back to the pantry to put the bowl down. It severely limits your execution speed no matter how fast the CP clock is actually ticking.
And that physical bottleneck is exactly what the register allocator, or the RMA, was designed to eliminate.
Okay, so how does it fix the pantry problem?
Well, the Mecrisp-RA, specifically version 2.5.4 used in this architecture, breaks the memory barrier by permanently hijacking the internal registers of the ARM Cortex-M4F processor.
Wait, permanently hijacking them?
Yes, it takes the top of stack, the absolute most critical piece of data the program is working with at any given millisecond, and it locks it permanently inside ARM register R6.
Oh, wow. So instead of walking to the pantry, the chef simply keeps their most important ingredient in their hand at all times.
Exactly. They never set it down in RAM. That eliminates the memory bus penalty entirely for the most frequent operations.
That's brilliant.
And it goes much deeper than just holding one item. The register allocator actively tracks 5 additional stack slots across other ARM registers. It maintains this highly complex internal model of the execution state.
So it's keeping track of multiple ingredients on the cutting board right in front of the chef.
Right. And for every single one of those 5 slots, the compiler tracks 2 vital pieces of metadata. First, the state of the data, meaning, is this value a known constant that was determined at compile time? Or is it an unknown value that will only be generated at runtime?
Okay, and the second piece of metadata.
If it is a known constant, the compiler tracks the actual numeric value itself.
Wait, if the compiler is tracking the numeric values of constants while it compiles, it can theoretically just solve the math before the program even runs.
That is precisely what it does. It's a technique called constant folding. And in a 20 kilobyte system, the implementation here is just remarkable.
How does that look in practice?
So suppose a developer writes a simple piece of logic, like 3 space 4 space plus. A naive compiler would generate machine code to push 3, push 4, and execute an add instruction.
Right, 3 distinct steps.
But the register allocator intercepts this. It sees the 3, it sees the 4. It looks at the addition operator and recognizes it as what it calls a two-foldable operation, an operation that takes 2 predictable constant inputs.
So it just does the math internally.
It executes the addition right there at compile time. It never generates a single ARM assembly instruction for the addition.
That's crazy. So no code is generated at all.
None. It simply calculates 7, updates its internal register model to note that a constant 7 is now sitting in the track stack slots, and moves on. When the program is actually deployed and running, that addition operation simply does not exist. The answer was pre-calculated.
It literally cheats time. The chef predicted your order and cooked it before you even walked into the restaurant. But code is rarely just static numbers, right? What happens when a constant interacts with a variable that can only be known at runtime? Say I'm reading a fluctuating temperature sensor, and I need to add an offset of 1 to the reading. The temperature is a runtime variable, but the 1 is a constant.
That is where the RA utilizes opcode optimization, which requires a really deep, intimate mechanical sympathy with the ARM Thumb2 instruction set.
Okay, mechanical sympathy. Explain that.
Thumb2 is a specialized instruction set designed for high code density. It allows certain small constants to be physically embedded directly inside the 16-bit or 32-bit machine code instruction itself. These are called immediate mode instructions.
Okay, let me map this out. If I didn't have opcode optimization, the compiler would have to generate an instruction to load the constant 1 from memory into a temporary register.
Right.
And then generate a second instruction to add that temporary register to my temperature reading.
Which consumes more flash memory and takes more clock cycles to execute.
Mm-hmm.
But the Mecrisp register allocator evaluates the constant value. If it sees that you want to add 1, it knows that the Thumb2 architecture supports adding small, immediate values directly.
So it folds it in.
Yes, it folds that constant 1 directly into a single adds instruction. It completely skips the load operation. And the RA is incredibly aggressive about this.
How aggressive?
It categorizes constant values based on their bit width. It can fold values into plus or minus 8-bit or 12-bit immediate add and subtract instructions. If you're doing bitwise logic, it can fold constants into 12-bit bit masks. It can even fold 5-bit integer amounts directly into hardware shift instructions.
Wow.
Yeah, it squeezes the logic down to the absolute smallest physical footprint the silicon will accept.
That explains the code density. It's packing logic at the molecular level. But Forth is famous for building complex programs by stacking hundreds of tiny, simple functions, which it calls words on top of each other.
Yes, that's the standard fourth paradigm.
Right. But in C, if you call hundreds of tiny functions, the overhead of jumping around memory usually kills your performance. Every time you call a function, the CPU has to save its current address, push a stack frame to memory, jump to the new function, execute it, pop the stack frame, and jump back.
It's a lot of thrashing.
Yeah. So how does Mecrisp-Cube avoid grounding in that branch and link overhead?
It utilizes automatic inlining, but it does so with a very specific lightweight heuristic. As the developer defines new fourth words, the compiler counts the number of generated machine code instructions. It tracks a variable called raw inline length.
Okay, so it's measuring the size of the function.
Exactly. If a newly defined word compiles down to 10 opcodes or fewer, and it terminates cleanly with a standard return instruction, the register allocator tags that word as inlineable.
Meaning, when I call that word later in my program, the compiler does not generate a jump instruction to go execute it.
It copies the actual raw machine code body of that tiny word and pastes it directly into the current execution stream. It physically flattens the code.
So the branch instruction vanishes.
The branch vanishes. The stack frame overhead vanishes.
But hold on, I see a major mechanical flaw here. We just talked about how the register allocator tracks those 5 stack slots and knows what constants are in them.
Right.
If the compiler is just blindly copy-pasting blocks of machine code into the stream, how does it not instantly lose track of the register state? The pasted code was compiled in a vacuum, right? It doesn't know what constants were sitting in the registers right before it was pasted?
You've identified the exact reason why single-pass compilers usually struggle with optimization. If the compiler lost the register state, it would have to assume all variables were unknown runtime values.
And then it would generate much slower, pessimistic machine code.
Exactly. The solution in Mecrisp-Cube is called the inline cache. The register allocator doesn't emit machine code immediately. It buffers the last 6 compilation steps in an internal memory array. It essentially delays the final generation of the code, giving itself a short-term memory.
It's looking ahead, or rather looking slightly into the past before it commits to writing the code.
Yes. When an inline word is triggered, this 6-step cache allows the RA to see past the boundary of the pasted code. It uses the buffered steps to propagate the known constant values across the inline boundary.
Oh, that's incredibly clever. So the state tracking survives the copy-paste operation.
It does. That inline cache is the architectural linchpin that makes cross-boundary constant propagation possible in a system that lacks a heavy multi-pass optimization pipeline.
And when you combine this memory-free stack tracking, the constant folding, and the boundary-crossing inline caching, the execution speed on the physical silicon has got to be staggering.
It really is, especially when you look at the hardware it's running on. The STM32WB5RG chip has a dedicated hardware single precision floating point unit, an FPU.
Right.
Because the register allocator has stripped away all the RAM access delays, data flows from the ARM core into the FPU registers with almost zero friction.
The results are mathematically profound, I imagine.
Absolutely. The system includes fourth words for complex trigonometry, like fissin for sine, or fex for exponential decay functions. Normally, executing those in an interpreted language is sluggish.
Yeah, because it has to translate everything.
But here, because the data pipeline is so tightly managed in registers, you're executing complex floating point math with near single-cycle efficiency. You are achieving performance that would typically require a senior engineer writing highly tuned, hand-crafted C code with strict compiler optimization flags.
And it is doing all of this from an interactive prompt that lives entirely inside 20 kilobytes. It is a stunning achievement. But we have to address the elephant in the room.
The maintenance?
Yes. This optimization pipeline sounds incredibly fragile. You mentioned earlier that Mecrisp-Stellaris RA isn't written in a high-level language. It's not written in C. It isn't even written in Forth, so it cannot compile itself.
No, it cannot. The entire kernel, including the compiler, the interpreter, and those deeply complex register allocator state machines we just detailed, is written entirely in hand-coded ARM thumb-assembly language.
Wait, all of it?
All of it. Matthias Koth, the original author of the RA, handwrote the silicon instructions to get the footprint down to 20 kilobytes.
That is... I mean, assembly language is the rawest form of human-readable code. It's just abbreviations for raw silicon commands. Organizing a project of this scale in assembly is incredibly difficult.
It's a monumental task.
I was looking at the source tree for this before we started. The main entry point file is called Mecrisp.s. Just the configuration variables and the dot include directives, the commands that tell the assembler which other files to pull in. Those alone take up 560 lines of text.
And that structure reveals a major vulnerability. Because this is a single-pass assembly project without a modern, sophisticated linker, the physical order in which those files are concatenated is the only way the system resolves memory addresses.
Oh, wow. So order is everything.
Yes. That Mecrisp.s file pulls in roughly 55 other assembly files in a brutally strict dependency order. If you look at files like RayCompilator.s or RayInfrastructure.s, you are looking at incredibly dense logic dictating that 6-step inline cache and the register tracking.
That presents a massive trust issue. State machines written in hand-coded assembly are notoriously difficult to debug.
They are.
But let's say I'm an engineer and I want to add a feature to the compiler. I dive into RayCompilator.s, I write some new assembly, and I make a subtle mistake.
Okay.
I accidentally create a condition where a stale constant value in that inline cache doesn't get invalidated when it should. What happens? Does the compiler throw an error? Does the system crash and give me a stack trace?
It doesn't either.
Really?
It simply produces silently wrong machine code. And that is arguably the most terrifying phrase in software engineering.
Silently wrong machine code.
Yes. The compiler will cheerfully accept your fourth code. It will execute the flawed assembly state machine. It will generate thumb-2 instructions, and the program will run without a single warning. But the math will just be wrong.
That's a nightmare. The FPU will calculate the wrong sine wave. The sensor offset will be incorrect. You would have absolutely no indication that the compiler itself is the source of the failure.
None.
If the compiler lies to you, how do you even begin to debug the error? I mean, in modern software development, if we modify a compiler or a critical library, we rely on massive automated testing pipelines.
We rely on CI/CD.
Right, continuous integration servers like GitHub Actions. Every time a developer commits code, servers automatically run thousands of unit tests, regression tests, and property-based fuzzing tests to ensure the logic still holds. What automated guardrails exist for Mecrisp-Cube?
There is an absolute, complete automated testing deficit. There are no unit tests validating the register allocator's state transitions. There is no CI/CD pipeline ensuring that a change in file number 42 doesn't silently break the inline cache in file number 12.
So how on earth does a developer verify that the machine code being generated is actually correct?
You're forced to rely on the only tool available in this environment: manual visual inspection through the interactive REPL.
The read evil print loop.
Exactly. Because the compiler is live on the chip, you write your fourth word, and then you type the command C followed by the name of the word you just created. The system dynamically disassembles the machine code sitting in flash memory and prints the raw ARM assembly instructions back to your terminal screen.
You literally have to read the machine code by eye.
By eye.
So you write a math function in fourth, type C, look at the raw hexadecimal memory addresses and thumb-2 opcodes scrolling up your terminal, and mentally calculate whether the register allocator allocated the registers correctly. That is not a workflow. That is an endurance test.
It places an immense cognitive load on the developer, and it raises severe questions about the long-term maintainability of the project. In the software industry, we often talk about the bus factor.
Right, the number of key developers on a project who could get hit by a bus before the project completely dies.
Exactly. For the core Mecrisp-Stellaris RA, the bus factor is effectively 1. The barrier to entry is astronomical. If a firmware engineer wants to contribute to the core memory management, they aren't reading high-level readable forth.
They're reading assembly.
They're parsing dense, highly intertwined ARM assemblies scattered across 55 concatenated files. If you make a typo, and the assembler throws an error on line 8423, you have to run grub searches across the entire directory structure just to figure out which physical file contains the error.
It's a maintenance nightmare. Which really begs the question, if the lack of automated testing, the silent failure risks, and this extreme barrier to entry make it a terrifying prospect for, say, writing software for an industrial robotic arm or a medical device, is the system just a fascinating dead end?
It seems like it would be, right?
Yeah, but actually, no. And this is the great paradox of Mecrisp-Cube. The exact same architectural decisions that discard modern build systems and automated tests create an environment that is an absolute superpower for STEM education.
That's the flip side. The interactive nature of the system completely subverts how we traditionally teach embedded engineering.
Walk me through that contrast.
To understand the contrast, look at the standard educational workflow for a beginner. A student sits at a PC, they open a massive IDE, write some C code, and click compile. They wait for the toolchain to build the binary. They use a hardware programmer to flash that binary over a cable to the microcontroller.
Right.
They reboot the board, open a serial monitor, and watch the output to see if the LED blinked. If they miss a semicolon or set the wrong bit in a register, they have to stop, go back to the PC, and repeat the entire multi-minute process.
The edit compile test cycle is painfully slow. I remember being in those university labs. You spend 90% of your time fighting the compiler and the flashing tool, and 10% of your time actually thinking about the hardware. It completely shatters the student's flow state.
Mecrisp bypasses all of that because it is entirely self-hosted. Once the kernel is flashed onto the target hardware the very first time, the PC is no longer compiling anything. The compiler is physically running on the Cortex M4F processor.
So the student just opens a terminal.
A student opens a simple terminal program, connects via USB, and types code directly into the chip. The edit compile test cycle is instantaneous. You type the command to turn a pin high, press enter, and the hardware reacts in milliseconds.
It turns the microcontroller into an interactive sandbox, and they don't even need to hunt down external data sheets on the internet to figure out how to use it, do they?
No, because the system ships with its own internal documentation. The board has a 384 kilobyte internal F8 flash drive, and inside that drive is a directory called man, containing 12 markdown files.
Like Linux man pages.
Exactly like that. It acts as a self-contained on-device textbook explaining the APIs, the hardware endpoints, and how to interface with the real-time operating system.
It democratizes hardware access. But a common question from educators is, if the system relies on such a complex, assembly-driven register allocator, do I have to teach my students ARM assembly language before they can even blink an LED?
And the answer is absolutely no. You can teach the abstract concepts of register management without ever exposing them to a single thumb-to instruction.
How do you do that without the students getting lost in the weeds?
You use intuitive physical analogies that mirror the silicon. Instead of using the old book on a desk metaphor, you teach them about predictive caching. You tell the student to imagine they are a bartender.
Okay, I like this.
A bad bartender waits for the customer to order, walks to the back room, gets a glass, walks to the fridge, gets the ice, and makes the drink sequentially.
Like the pantry analogy from earlier.
Exactly. A good bartender, which represents our register allocator, predicts the state. They already have the shaker in their hand, and the 3 most popular bottles lined up on the rail in front of them. You explain that the CPU register is the bartender's hand, and the RAM is the back room.
So the compiler's entire job is to predict what data you need and put it in your hand before you ask for it.
Right. It demystifies what a compiler actually does.
Let's put this into practice. If I'm an educator, how do I structure a lab module around this interactive workflow? Let's say the goal is for a beginner student to build a functioning IoT sensor data logger from scratch. Walk me through the lesson plan.
The lesson plan leverages the immediate feedback loop of the REPL. Step 1 focuses purely on the stack mechanics. The student connects to the terminal. They type numbers and operations like 5 space 10 space plus space period.
And the period is the 4th command to print the top of stack.
Yes. Instantly, the terminal prints 15. They experiment with postfix notation and see the results instantly, building mental models of how data moves.
That's step 1.
Step 2 introduces physical hardware. The student wires an analog light sensor to a pin on the board. They type a single command, a pin in it which stands for analog pin fetch. They hit enter, and the terminal immediately prints the raw voltage value.
There's no C boilerplate at all.
There is no peripheral initialization code required from the student. They just demand the data from the silicon, and the silicon provides it.
That is an incredible aha moment for a beginner. The hardware responds instantly, but raw data isn't enough, right? A data logger needs to know when the event happened.
Which leads to step 3. You introduce the real-time clock peripheral. The student uses the time bang command to set the current time and the timer command to read it back. Now they can pull a sensor reading and pair it with a timestamp.
Okay, and step 4.
Step 4 introduces data persistence. The student interacts with the built-in FAT file system. They learn how to open a text file on the internal flash drive, format their timestamp and sensor reading into a string, and append it to the file. They're essentially building a localized database.
And what if they want to retrieve that data without plugging the board back into a laptop? You mentioned the STM32WB55RG has a Bluetooth radio. Can a student actually interface with a modern BLE stack through this tiny terminal?
Yes, and that's step 5. It connects the system to the outside world. Mecrisp-Cube abstracts the STMicroelectronics BLE middleware. The educator instructs the student to use the specific forth commands to broadcast their log data over the cable replacement service, or CRS.
So they just use CRS.
Right. The student can literally pull their smartphone out of their pocket, open a standard Bluetooth terminal app, and watch their sensor data stream wirelessly from the board they just programmed.
So in a single 2-hour lab session, a student goes from not knowing what a stack is to holding a fully self-contained wireless IoT edge device that they built and programmed interactively.
They didn't just paste code into a library. They interactively queried the hardware at every step.
It creates a tactile connection to the embedded environment that cross-compiled C code simply cannot replicate.
It really is a game changer for education.
But hold on, bridging that gap between the fourth kind and the actual silicon is historically very messy. We know that modern ARM Cortex-M peripherals, like the analog-to-digital converters, the I2C buses, the Bluetooth radio, are intensely complicated.
Extremely complicated.
To control them, STMicroelectronics provides a massive hardware abstraction layer, the HAL, written in C. It is thousands of files and millions of lines of code designed to handle every hardware edge case.
Right.
Mecrisp-Cube obviously doesn't have the memory to rewrite a thick HAL in forth. So how does a 20-kilobyte assembly kernel physically talk to this complex hardware?
Well, Peter Schmid, the creator of the Mecrisp-Cube integration, took a very pragmatic approach. He recognized that rewriting ST's massive HAL in forth was impossible, so he built a remarkably thin C interface.
How thin?
Very thin. Forth and C operate in different paradigms, but they both ultimately run on the same ARM processor and use the same registers. Schmid mapped the forth system so that it could interoperate bidirectionally with standard C functions, utilizing raw register conventions with zero marshalling overhead.
So it's using that same branch and link, the Boolean instruction that we talked about earlier.
Exactly. Any C function compiled by the GCC toolchain that takes its arguments in ARM registers R0 through R3 can be directly executed by the forth kernel.
So when the student in the lab typed a pinat to read the sensor,
the forth word simply executed a hardware branch instruction into a custom C driver located in a directory called peripheral/.
Oh.
The C driver interfaces with the thick STHAL, manages the complex peripheral registers, reads the sensor, and places the final value in register YOOO. The C function returns, and forth seamlessly moves the value from R0 directly into its top of stack register, R6.
It's an incredibly tight handshake. But combining an interactive REPL with a real-time system introduces a massive timing vulnerability. Let's look at interrupts.
Okay, let's look at them.
Say I'm typing in the forth terminal. The register allocator has cached my variables in register R6 and the other stack slots. Suddenly, a physical Bluetooth packet arrives at the antenna. The hardware triggers an interrupt, demanding immediate CPU attention. The hardware jumps into the C interrupt service routine to handle the radio. Doesn't that C routine instantly overwrite the CPU registers, completely destroying forth's stack state?
In a purely bare metal system without an operating system, yes. That would be a catastrophic data corruption event. The interrupt would clobber R6, and when forth resumed, it would be operating on garbage data. But Mecrisp-Cube integrates FreeTS, a widely used real-time operating system.
So FreeTS manages it.
FreeTS acts as the safety net that prevents C and forth from destroying each other.
How does FreeTS mediate that context switch?
When you write a forth program that needs to wait for a hardware event like waiting for a button press or a radio packet, you do not write an infinite loop that burns CPU cycles.
Right, because that would lock the system.
You use a thin forth veneer command called xewait. This command instructs FreeTS that the forth task is going to block on a semaphore. FreeTS immediately puts the forth task to sleep. But before it does, it takes a snapshot of the CPU.
A snapshot of the registers.
Yes. It saves all of forth's registers, including the critical R6 and the other stack slots, into a specific memory structure called the tasked control block.
Okay, so forth state is safely frozen in memory.
Exactly. The CPU is now free. When the hardware interrupt fires, the C interrupt routine handles the Bluetooth packet and then gives the semaphore. FreeTOS sees the semaphore is available, wakes the forth task back up, and fundamentally restores the CPU state from the task control block.
So register R6 is perfectly reinstated.
Yes. And forth resumes execution entirely unaware that it was even asleep. FreeTOS guarantees the memory boundaries between the two paradigms.
That is architectural elegance. But it introduces a workflow problem. The core C wrappers and peripheral drivers live in the STM32 Cube ID ecosystem, while the custom fourth logic lives on the internal FAT file system.
Right. Two different storage areas.
If a developer needs to update a peripheral driver, say ST Microelectronics issues a critical bug fix for their I2C hardware driver, how do they manage that update without wiping out all the custom fourth code they wrote interactively?
The dual-layer architecture actually protects the developer here. To update the low-level C plumbing, you do have to exit the interactive REPL. You must open STM32 Cube IDE on a host PC, pull the new driver, recompile the entire core C wrapper along with the assembly kernel, and reflash the physical microcontroller over USB.
Which wipes the flash.
Yes, but, and here is the key, because the developer's high-level custom application logic is saved as text files on the dedicated FAT file system partition, it completely survives the reflashing process. The kernel and the C drivers are updated underneath, but the fourth application remains untouched and ready to execute the moment the board reboots.
It separates the hardware plumbing from the business logic. That's smart. Now, I want to talk about my absolute favorite mechanical feature of this system, the multi-terminal I/O architecture.
So very unique.
When I read the source material, this felt like science fiction for an embedded device. How does it handle input and output dynamically?
It utilizes dynamic hook pointers, which fundamentally alter how data routing works. In a standard C application, if you call print, the output is usually hard-coded by the linker to a specific hardware interface, like a single UART serial port.
So if you want to change where print sends data, you have to rewrite the code and recompile.
Exactly. But in Mecrisp-Cube, the core fourth, words for input and output key for reading a character and emit for writing a character do not talk directly to hardware.
They don't know what a UART or a USB port is.
No. They simply look at a memory pointer stored in the user area of the current FreeRTOS task.
I picture this like an old-school telephone switchboard operator. The fourth program doesn't yell directly into the USB cable. It hands a message to the switchboard operator, the pointer, and the operator can plug that message into whatever hardware port is currently requested.
That is a perfect analogy.
Yeah.
And the brilliance is that the operator can change the physical plug at runtime, dynamically, without stopping the program.
You don't have to restart it.
No. You can execute a command to point emit to the UART driver, which utilizes a 5 kilobyte interrupt-driven ring buffer. A second later, you can point it to the USB CDC driver to stream data over a USB cable.
Wow.
A second after that, you can point it to the BLE CRS interface, broadcasting the terminal output wirelessly. You can even route the command line output directly to a tiny OLED screen attached to the board.
Let's contextualize this. Paint a picture of a developer utilizing this hot-swapping terminal for live hardware debugging in the field.
Okay, let's assume you're an engineer tasked with debugging a complex environmental sensor node that has already been physically mounted to the ceiling of a warehouse.
Okay, it's out of reach.
You start at your desk. You connect the board to your laptop via USB. The system auto-detects the USB CDC connection and routes the switchboard operator there. You interactively write and test your fourth code to query the I2C temperature sensor. You verify the math is correct.
So far, standard bench work.
Right. You then take the board and bolt it to the ceiling. You can no longer plug a USB cable into it. You climb down the ladder. But you still need to test it under real environmental conditions. So you pull out your smartphone, open a Bluetooth terminal, and connect to the board's BLE CRS interface. You type a single command, char submit.
The switchboard operator unplugs the USB cord and plugs into the Bluetooth radio.
Immediately, the command line interface relocates to your smartphone screen. You are now communicating with the live RTPL wirelessly.
That's amazing.
But the debugging power goes further. If the sensor suddenly stops responding while mounted on the ceiling, you don't have to unscrew it and take it back to the lab. Right from your phone over Bluetooth, you can type raw fourth commands to physically toggle the I2C clock and data pins high and low.
So you can wiggle the bus lines manually, live in the field to see if the hardware peripheral is electrically locked up, all without recompiling or rebooting the core system.
Yes, it is the ultimate prototyping and diagnostic tool.
It really is. But we have to be objective here. Let's take Mecrisp-Cube out of the classroom, out of the hobbyist's hands, and place it in a corporate, commercial firmware factory. Does this ecosystem actually belong in a professional engineering firm? We need a corporate reality check.
If we're evaluating this for commercial deployment, we have to strip away the enthusiast appeal and look at hard metrics. First, let's compare the performance of this native fourth against the other darlings of the modern embedded world. Interpreted MicroPython and compiled Rust.
Let's start with MicroPython.
When pitted against MicroPython, Mecrisp is vastly superior in terms of raw execution speed and resource efficiency. MicroPython executes bytecode inside a virtual machine and treats everything as an object, which introduces massive memory overhead and garbage collection pauses.
Right.
Mecrisp, utilizing the register allocator and generating raw Thumb2 machine code, routinely executes 10 to 50 times faster than MicroPython, while consuming a fraction of the flash memory. If you have a strict power budget or a tiny microcontroller, MicroPython will choke where Forth will thrive.
Okay, so it easily beats Python on speed and size. But what about Rust? Rust has taken the embedded world by storm, specifically with frameworks like Embassy.
Rust offers comparable and often slightly better execution performance because it is backed by the massive, highly optimized LLVM compiler infrastructure running on a powerful host PC.
Right, it's doing heavy lifting before it ever hits the chip.
Exactly. Rust obviously lacks the interactive REPL. But execution speed is not why Rust is winning the commercial sector. Rust completely destroys Forth in the one metric that high-stakes commercial engineering values above all else: safety.
We're talking about memory safety. Forth offers absolutely zero guarantees.
None whatsoever. In Forth, you are manually managing stack pointers and raw memory addresses. If your logic is flawed and you pop one too many items off the data stack, or if you write to an uninitialized memory pointer, the system will not stop you.
It'll just do it.
It will silently corrupt adjacent memory, overwrite the RTOS structures, or hard fault the CPU. Rust compiler, through its Bartow checker, mathematically guarantees memory safety at compile time.
And when you analyze the architectural risks of Mecrisp relying on a developer to manually track stack depth, combined with an assembly-based register allocator that we already established can produce silently wrong machine code, it fundamentally fails to meet the strict certification requirements of high-stakes industries.
It does.
If you're building a pacemaker, an automotive braking system, or an industrial robotic arm, you have to comply with standards like MISRA-C.
Certification bodies require formal verification. They require automated test suites proving that the compiler behaves predictably under all edge cases. You cannot run life-critical hardware on a brilliant but unverified handwritten state machine. The risk of catastrophic failure and the resulting liability is simply unacceptable for a commercial firm.
But let's say we aren't building a pacemaker. Let's say we're a startup building a simple consumer smart home device, like a smart toaster. Safety isn't life or death. What about the tooling? How does this architecture fit into a modern software company's development workflow?
It creates immense friction due to severe build system limitations. Earlier, we praised the system for being self-hosted. That is only true for the high-level Forth code.
Right.
The underlying C infrastructure, the hardware abstraction layer, and the free TOS integration are completely locked into the proprietary STM32 ID ecosystem.
Meaning the project relies on the graphical Eclipse-based IDE to compile the kernel.
Exactly. There are no standalone makefiles or CMake scripts provided. There is no native compatibility with standard CI/CD continuous integration and continuous deployment pipelines.
If a team of 10 engineers tries to use this, they can't just push their code to a GitHub repository and have a cloud server automatically build the firmware, run static analysis, and execute hardware-in-the-loop tests.
No. And the practical workflow for managing the custom C code within this hybrid project is a deeply frustrating experience.
Why is that?
If an engineer needs to change a hardware pin mapping, say moving an LED from pin A to pin B, they have to open the graphical STM32 IDE, they open the visual QMX configuration tool, change the pin, and click Generate Code.
Right, that's the standard ST workflow.
But CubeMX is notorious for its aggressive code generation logic. It frequently and blindly overwrites custom C files, replacing the careful Mecrisp integration logic with generic ST boilerplate.
Oh man, so the visual tool actively breaks the project every time you try to configure the hardware. How does a developer actually work around that?
The developer is forced into a fragile workaround. They run the visual code generation fully expecting it to break the project. They then have to drop into the command line interface and manually execute git commands like git checkout -- peripherals / to selectively restore the custom C files that CubeMX just destroyed.
That sounds incredibly tedious.
It is. They have to hope that this manual restoration doesn't introduce merge conflicts with the new pin definitions. It is a highly manual, irritating process that breaks automation and introduces massive opportunities for human error.
So when we assess what the commercial industry actually requires for code maintenance, this niche tooling falls drastically short.
Unfortunately, yes.
Commercial firmware environments don't just require speed, they require scalability. They need massive package ecosystems, predictability, automated regression testing, and CI/CD pipelines. They need the assurance that if senior developer A leaves the startup, junior developer B can come in, read the C or Rust codebase, run the automated test suite, and push a firmware update with absolute confidence that they didn't break the product.
And that's exactly right. The software industry standardized on high-level languages and heavy tool chains not because they are inherently faster or more elegant at the silicon level. They standardized on them because they are predictable and scalable across large teams of humans.
Yeah.
Mecrisp is a work of undeniable isolated genius, but it requires every user who touches the core architecture to operate at that same level of isolated genius without a net.
Which brings us perfectly to the summary of this entire deep dive. Mecrisp represents a profound architectural duality. On one side, it's an absolute engineering masterpiece. It is a brilliantly optimized native code system. The way the register allocator bypasses the RAM bottleneck by holding the top of stack in register R6, the way it cheats time with constant folding, and the way it hot swaps terminal output for live hardware debugging without ever cross-compiling, it is a superpower.
It is a love letter to the raw capabilities of bare metal embedded hardware. It proves exactly how much logic, performance, and interactivity you can achieve with just 20 kilobytes if you possess a deep mechanical sympathy for the silicon.
But on the other side, it is a glaring cautionary tale. It highlights exactly why the global software industry moved away from handwritten assembly state machines and eagerly embraced the massive, heavy, gigabyte-sized tool chains we complained about at the very beginning of the show. The risk of silent mathematical failures, the total lack of automated testing, and the inability to scale across an engineering team are the exact reasons we endure the burden of modern abstraction.
It forces us to confront the trade-offs we've universally accepted in the name of safety, predictability, and convenience.
And that leads me to a final thought I want to leave you, the listener, to mull over as you go back to your day. We live in an era where we casually throw megabytes of RAM and gigahertz of processing power at the absolute simplest problems, like reading a temperature sensor or blinking a smart bulb. Have our safe, high-level languages and automated testing suites actually blinded us to the true, raw capabilities of the silicon sitting on our desks? If a system can run a native compiler, a real-time operating system, a Bluetooth network stack, and a file system in just a fraction of the memory it takes to load a single modern web page, what does that say about the state of modern software bloat? If you were forced tomorrow to build your next major project using only 20 kilobytes of memory, what layers of modern abstraction would you suddenly realize you never actually needed?
It's a question that challenges the foundation of modern software engineering.
Thank you so much for joining us on this deep dive. We highly encourage you to go explore the source material, read up on the history of Forth, and maybe even flash a microcontroller yourself to experience the REPL firsthand. Until next time.